71% of Earth's surface is ocean. Average depth, 3,682 meters, the deepest point ever measured, the Challenger Deep. Sits 10,925 meters down, reached solo, in a titanium submersible called Limiting Factor by the explorer Victor Vescovo in 2019. That's close to the cruising altitude of a long-haul jet, pointed the other direction. And if every molecule of water on this planet vanished in the next second, you would not live long enough to finish reading this sentence. You are roughly 60% water by mass. Your neurons fire using electrochemical gradients that require liquid water to exist at all. Take the water out of a synapse, and the synapse doesn't slow down. It stops. So let's be precise about what we're actually asking, because precision is the entire point of thinking about this instead of just reacting to it. When people picture Earth's water disappearing, they picture almost the same scene every time. The oceans drain away. You're left with a rusty, cratered, Mars-shaped rock and everything else about the planet. Its rock, its air, its temperature, its oxygen supply carries on roughly the way it does now, just without anything wet in the picture. Water gets filed away as a topping. Something poured onto an otherwise finished planet, sitting on top of the real geology, the real atmospheric chemistry, the real biology, without being load-bearing in any of them. It's an understandable mistake. Water is the one substance on this planet you can watch, touch, and swim in. So it's easy to assume you're already seeing the whole job it does. That belief is what this video is going to take apart, piece by piece, because it's wrong in at least 4 separate, checkable ways. And the first one breaks about 400 kilometers under your feet. In 2014, a geochemist named Graham Pearson at the University of Alberta was part of a team studying a rough, flawed diamond that had been panned out of a riverbed near Guiana in Brazil. The kind of stone normally too full of internal defects to bother cutting into jewelry. Those defects are exactly what made it valuable to science. Trapped inside, it was a microscopic inclusion of ringwoodite, a high-pressure form of the mineral olivine that only forms under conditions found in Earth's mantle transition zone, a layer of rock between roughly 410 and 660 kilometers down. That crystal had never touched surface water. It couldn't have picked up any on the way up, sealed as it was inside one of the hardest materials on the planet. When Pearson's team analyzed it, they found it was roughly 1.5% water by weight. Not liquid, but hydroxide, chemically bound directly into the mineral's crystal structure. That number sounds small until you multiply it across how much rock actually exists at that depth. If the transition zone holds anywhere close to that concentration throughout, there's an estimated volume of water down there approaching, and by some calculations exceeding, everything currently sitting in every ocean on the surface combined. Not in a cave, not in an underground sea, welded into the rock itself, the way water gets trapped inside gypsum. Water was never decorating this planet. It's mixed into the recipe. So does that buried water actually do anything? Or is it just a 400-kilometer deep geological curiosity? It does something enormous, and it may explain why this is the only planet in the solar system currently running plate tectonics the way we define them. Venus is close to Earth in size and bulk composition, but its outer shell doesn't break into moving plates that slide beneath each other. Geologists call this a stagnant lid, one continuous, unbroken shell of rock. Earth's crust does something Venus's apparently doesn't. At ocean trenches, old slabs of seafloor bend downward and sink into the mantle, dragging hydrated minerals with them. The reaction has a name: serpentinization, where water reacts with mantle minerals like olivine and produces a softer, slipperier mineral called serpentine, which is part of why a subduction zone can bend at all instead of snapping. That water also lowers the melting point of the surrounding mantle rock and weakens it mechanically. A hydrated fault slides where a dry one locks up. Geodynamicists who model this for a living have found that hydration can be the difference between rock strong enough to grind a plate boundary to a halt and rock weak enough to keep it sliding. Without that lubrication, on the leading hypothesis, The mantle underneath us doesn't bend easily enough to subduct. And subduction is the process that recycles carbon, raises mountain ranges, and has been regulating this planet's temperature for billions of years by controlling how much carbon dioxide gets buried versus released back into the sky. Water isn't a passenger riding along on this machine. It may be the lubricant that lets the machine turn over at all. Delete the water, including what's chemically bound inside the mantle, not just what's sitting in the oceans. And you're not looking at a slightly drier Earth. Over geological time, you're looking at Earth sliding toward Venus's tectonic regime. A single rigid shell, no subduction, nothing getting recycled, but geology takes millions of years to show its hand. Something changes before you'd even finish saying the word overnight, and it happens to the color and temperature of the sky itself, for a reason that gets flattened into a small lie almost every time the greenhouse effect gets explained in a classroom. Ask a reasonably well-informed adult what causes it, and you'll get one answer nearly every time: carbon dioxide. That's not false. It's just badly incomplete. When a team at NASA's Goddard Institute for Space Studies, Andrew Lasis, Gavin Schmidt, David Rind, and Rita Rudy, sat down in 2010 and actually calculated which gases were doing the radiative work in Earth's atmosphere, they found that water vapor and clouds together account for roughly 75% of the planet's total natural greenhouse effect. Carbon dioxide and the rest of the non-condensing gases make up the other 25. Water is not a supporting character in the greenhouse effect. It is most of the greenhouse effect, wearing a carbon dioxide costume in almost every explanation of it you've ever heard. There's a reason water vapor is this good at the job, and it isn't mysterious. The water molecule is bent, not straight, which gives it an uneven distribution of electric charge across its shape. That lopsidedness lets it absorb and re-radiate infrared light, heat. At close to the wavelengths, Earth's surface glows in after dark. Carbon dioxide does the same trick in narrower bands. Nitrogen and oxygen, which together make up around 99% of the atmosphere by volume, do almost none of it, because their molecules are straight, symmetric, and largely transparent to infrared. The greenhouse effect isn't a property of the atmosphere in general. It's a property of a small minority of oddly shaped molecules inside it, and water is the largest shareholder by a wide margin. The same GIST team then ran an experiment that makes the dependency uncomfortably obvious. And it's worth being precise about what they actually did, because they didn't touch the water. They deleted the non-condensing gases instead, the carbon dioxide, methane, and ozone that don't rain out of the sky. Inside their climate model, then watched what water vapor and cloud cover did on their own once that support was gone. Within a single year, global average temperature had already fallen by 4.6 degrees Celsius. By year 50, it had dropped to 21 degrees below zero, a fall of nearly 35 degrees from where we sit today. And global sea ice cover had gone from under 5% to nearly half the planet. Nobody deleted the water in that experiment. Water deleted itself the moment everything holding it up was taken away. I want to be honest about something here, because I used to get this backwards myself. I treated the greenhouse effect as fundamentally a carbon dioxide story, with water vapor as background humidity. Present, sure, but not the main event. That's the wrong way around. And underneath it, there's a real gap I don't think anyone has closed. Nobody has cleanly modeled the specific scenario we're actually discussing tonight. Instantly deleting all atmospheric water and measuring the response in real time, rather than removing carbon dioxide first and watching water vapor follow it down over a year, the way the GIST experiment did it. Every climate model in existence treats water vapor as a fast feedback that reacts to other conditions, not as a variable you delete outright and observe in isolation. So the honest answer to exactly how many degrees, how fast, in the first hour is nobody has that number, because nobody has needed one before. That's not a hand wave. That's an actual, specific hole in an extremely well-studied field. What we can say with much more confidence is what happens to the organisms making your next breath possible, And that part of the story reassigns credit that almost everyone has misfiled. Ask most people which ecosystem is most responsible for the oxygen in Earth's atmosphere, and they'll say rainforests. The Amazon gets called the lungs of the Earth constantly, including by people who should know better. Measure it properly, and the credit shifts to somewhere almost nobody pictures: the open ocean. Marine phytoplankton, microscopic, floating, invisible from a boat deck, are responsible for something close to half of all the photosynthesis happening on this planet, despite making up less than 1% of Earth's total plant biomass. Meanwhile, on land, most of the oxygen a mature forest produces during the day gets consumed right back by that same forest at night and through decomposition, which is why a rainforest's net contribution to the atmosphere's oxygen budget, averaged across a full year, sits close to zero. It isn't producing nothing. It's producing and reabsorbing almost all of it in a closed loop. The ocean's version of that loop leaks. Dead phytoplankton sink, and a fraction of that organic carbon gets buried in seafloor sediment before decomposition can claw the oxygen back out of the atmosphere. That leak, repeated for roughly 2.5 billion years since oceanic cyanobacteria first started producing oxygen in bulk. The event geologists call the Great Oxidation Event, is the actual mechanism that stocked this planet's atmosphere with free oxygen to begin with. Delete the water, and you don't just lose the rainforest everyone worries about. You shut off the mechanism that's been quietly restocking the atmosphere's oxygen shelf for 2.5 billion years, using a leak nobody notices, because it happens in the dark, one dead microorganism at a time. Follow the timeline further forward, and the ocean floor itself doesn't just sit there, exposed and inert. It starts moving vertically, for a reason that has nothing to do with tectonic plates colliding. Right now, roughly 1.3 billion cubic kilometers of water is pressing down on the world's ocean basins, and that weight matters. Remove it, and the crust beneath does what any elastic material does when you take a load off it. It rebounds, slowly, over thousands of years. We've already watched a smaller version of exactly this. Parts of Scandinavia are rising out of the ground right now, measured by GPS at close to a centimeter a year in places, because the ice sheets that used to sit on top of the region finished melting roughly 10,000 years ago, and the crust underneath is still catching up. There's a second consequence of removing that weight that's easy to miss, because it isn't really about the crust rising. It's about what happens underneath it. When a heavy load is lifted off the mantle, the drop in pressure lets buried rock melt more easily, the same way water boils at a lower temperature on a mountaintop, where there's less air pressing down on it. Geologists have measured this directly in Iceland. In the few thousand years after its ice sheet retreated, roughly 12,000 years ago, the average rate of volcanic eruption there was, by some estimates, 20 to 30 times higher than it is today, driven almost entirely by decompression melting in the mantle underneath the vanished ice. Do the equivalent thing to every ocean basin on Earth at once, and you're not just describing a planet whose coastlines rise. You're describing a planet entering the largest, most simultaneous episode of decompression volcanism in its geological history. Global instead of local, running on the exact same physics already measured, in miniature, in Iceland. Empty every ocean basin on the planet in one stroke, and you'd trigger a version of that rebound at a scale nobody has ever measured, because nobody has ever unloaded that much weight off a solid planet's crust in a single event. The comforting picture has a drained, static bathtub sitting under an unchanged sky. The actual picture has a planet's entire crust unclenching in slow motion for millennia. All of this should change how you feel about a number astronomers throw around constantly. How many planets sit inside their star's habitable zone, the orbital distance where liquid water could theoretically exist on a surface? That number gets treated as a finish line. It's closer to a starting gate. A habitable zone planet with surface oceans still has to do everything. Earth's water has been quietly doing this entire video. Get subducted into its mantle in large enough quantities to weaken the rock and keep some kind of plate recycling running. Stay suspended in the air as vapor in exactly the right amount to sustain a greenhouse effect strong enough to keep the ocean from freezing solid without producing so much greenhouse effect that the whole thing boils away in the other direction, the way it likely did on Venus, and get consumed by something photosynthetic in enormous volume for billions of consecutive years to build an atmosphere with enough free oxygen for energy-hungry, complex life to exist at all. Surface water is the easy part to detect from light years away, in the wobble of a distant star's spectrum. Water doing all three of those other jobs at once, for billions of consecutive years, without the whole system tipping into a Venus-style runaway or a Mars-style freeze-out, is very likely the rare part. We've spent decades treating the presence of an ocean as the headline discovery. The headline was never the water sitting there. It was the water working. That's the actual stakes of the question we started with. It was never really, what happens if the oceans drain? It's how many separate, mostly invisible jobs is water doing on this one planet at once that nothing else nearby is doing anywhere. And the number is at least 4. Mantle lubricant, atmospheric thermostat, oxygen factory, and, yes, ocean. Take away any single one of those 4, and you don't get a slightly worse version of Earth. You get a fundamentally different kind of planet, and we only have one working example of what happens when all 4 keep running together. None of this needed a vanishing act to matter, either. All 4 jobs are running right now, quietly, underneath a headline that only ever mentions the ocean. Every wrong guess about this topic. The dead Mars rock, the rainforest getting the credit, the carbon dioxide-only explanation of the sky, comes from the same habit, crediting the part of the system you can actually see. The ocean was never the water. It was just the part of the water you happen to be able to see.